All right, hello, welcome to this week's weekly review from Math 2414. This week we're going to be covering sections 11.1 and 11.2. So section 11.1 is going to be over sequences, 11.2 is series. All right, so let's go ahead and get started with section 11.1. All right, so first off, a sequence. The definition of a sequence is going to just be a list of numbers with a definite order. And these can be listed out like in something such as this. So we have like a sub 1, a sub 2, a sub 3, a sub 4, and so on and so forth to a sub n. And this can be written as something as saying like we have these sets, like the curly brackets of a sub n. And we can also rewrite this as the set of curly brackets of a sub n beginning from n equals 1 to infinity. So like an example of this could be, for example, like using actual numbers, could be something along the lines of 1/2, 1/4, 1/6, 1/8, 1/10, and so on and so forth. So if we look at this right here, we can actually, so in this little pattern that we, in this little sequence that we just wrote out, we can kind of notice a pattern. So something that's important to know is that not all, but some sequences can be written as formulas, can be written as formulas. So one thing that we notice, so for example, in this one, what we can do is we can actually rewrite this as saying as a sub n is equal to 1 over 2n. And when we do this, we start off with n equals 1. So for example, if we were to list them at n equals 1, we'd get 1/2. N equals 2, we'd get 1/4. N equals 3, we'd get 1/6. And we can see how we're going to keep following this pattern. And just kind of like, for example, whenever you're writing like sets and stuff, like remember like whenever, sometimes when you try to like define like, when you're doing trig and you have something like, oh, we have to talk about every angle, like where this hits, and like and whenever it repeats and repeats, so you have to usually put like plus like n something. So in this case, n will always be an integer. So let's go ahead and try like a quick example of this, just to kind of get used to like getting in terms of formulas to terms and terms to formulas. So in this example, we're just going to list the first 5 terms. And in this one, we are given this sequence a sub n is equal to 1 over n plus 1 factorial. All right. So for those of y'all who are not familiar with factorials, essentially it's what you do is you take your number and you multiply it by each integer like by itself and below it. So for example, you do like if you have n factorial, that is equal to n times n minus 1 times n minus 2 times n minus 3, and then so on and so forth until you get all the way down to 1 pretty much. So in this example, so we're going to list our first 5 terms. So then let's go and just write these down as a sub 1, a sub 2, A3, A4, and A5. So we can go ahead and just plug in our n for each one of these. So we can get 1 over 1 plus 1 factorial, 1 over 2 plus 1 factorial, 1 over 3 plus 1, 1 over 4 plus 1, and lastly 1 over 5 plus 1. All right, so now of course we can go ahead and simplify these, so we can get 1 over 2, 1 over 3, 1 over 4, 1 over 5, and lastly 1 over 6 factorial. So what we're going to do now is we're going to go 1 over 2 factorials, 1 over 2 times 1, so this is just going to be 1/2. 1 over 3 factorial is going to be 3 times 2 times 1, so that's going to be 1/6. 4 factorial is going to be 1 over 4 times 3 times 2 times 1, so 1 over 24. 5, 1 over 5 times 4 times 3 times 2 times 1, so 1 over 120. And lastly, 6 factorial, it's going to just be, I'm going to simplify this, 6 times 5 factorial. So 1 over 6 times 120 is 1 over 720. So therefore, these are going to be our first 5 terms within this sequence. So now let's try another one. So now let's try going from terms to a formula. So in this example, we want to find the formula for A sub n, and we are given the terms -3 to -4/3, 8/9, and -16 over 27, and we're just going to kind of, pretend we're going to keep going. All right, so now we have to go ahead and let's notice some things within the sequence. We can notice that we are alternating from positive to negative. So whenever you see that, you know that you're going to have a -1 to something. We're not going to say exactly what yet. We're going to have to play with that, but it's going to be -1 to something. And then now let's also look and see. We can see we have powers of 3. So we go from 3 to 1 to 1/3 to 1/9 to 1 over 27. So from here, it looks like that we're decreasing by a power of 3 each time. And similarly with 2, it looks like we have 1 to 2 to 4 to 8 to 16. So, and that looks like we're increasing by an order of magnitude by 2. So let's go ahead and look and see. So if we're decreasing by 3, by order of 3 each time, we can say that we're going to be multiplying 1/3 times each term. Now, where we start, we all get to that in a minute. And we can also see we're multiplying times 2 with each term as well. So we have these 3, so we know we have these 3 pieces, and these should get to like what we have. But now we need to figure out exactly what our exponents are. So our -1, so we can see that our first term is going to be negative, and then so -1 to the first power would be negative. The -1 squared would be positive, just like our second term. -1 to the third, it would be negative again. So therefore, we can actually just say that we're going to have n as our first exponent, because that matches our order of how we're going from negative to positive to negative again. So now we have the 1/3. So we also have to remember that we're starting off with n equals 1. And we're starting off with 1/3 to the -1, correct? So therefore, we know that we have to get something, we have to somehow get from 1 to -1. So therefore, what we can do is we can put n minus 2 for our exponent for 3, because if we start off with n equals 1, we get -1 and our exponent right there. And then for 2, we also have to figure out a way to get from, we start off with 2 to the 0. So therefore, what we can do is we can do n minus 1 to get us started off in the right spot. So therefore, our final formula will be a sub n is equal to -1 to the n times 1/3 to the n minus 2 times 2 to the n minus 1. All right, so let's say we want to go ahead and try to plot some points. One example that we can do is let's go ahead and use that 1 over n plus 1 factorial. Let's say we want to plot this on a graph. We're going to go and just do 1/2 up here, 1/4, and 1/8, and then we have 3/8 right here. All right. So remember our first 5 terms were, our first 5 terms just again were 1/2, 1/6, 1/24, 1 over 120, and 1 over 720. So let's go ahead and plot those points. 1/2, and then, all right, let me go and just draw like a little axis down here. So we're going to have 1, 2, 3, 4, 5. All right, so if we plot these points, we go ahead and we start off at 1/2, and we move down to 1/6, which is going to just put about right here. 1 over 24th, we're going to go ahead and put right here. For our fourth one, we get 1 over 1/20th, so we're getting really close. And then 1 over 7/20th, looks like we can't really draw it that well, but we are just over the line. So when we look at this, we can see that our terms are getting smaller and smaller and smaller. And what we can also notice is that, so what we can actually say is that the limit, when we can see if this is going to approach 0, because if we think about it, our numerator is always going to stay 1. Our denominator is going to get increasing and increasing and increasing, but there's no way we're ever going to get a negative to cross that. So what we can do is we can actually say that our limit as n approaches infinity of 1 over n plus 1 factorial is equal to 1 over infinity, which is 0, which makes sense. So that brings up the idea of convergence and divergence. So we have actually already talked about this a little while ago, I believe, when we were doing improper integrals. So the concept is pretty similar. So for a sequence to be convergent, the limit as n approaches infinity of a sub n, so like the infinite term in that sequence, must equal some finite number L. Or we can think of this as our infinite term approaches L as n approaches infinity. And if this is not the case, our sequence is divergent. So yeah, once again, this is pretty similar concept to what we've been doing. So let's go ahead and keep moving on. So this one is just kind of a dense section. There's just a lot of like things we need to know about. So another piece that they did talk about in your textbook, I'm not going to really go into a ton of detail on this since this is pretty similar to review. Our limit laws are essentially the same for sequences and functions. So if you go way back to early 2413 when we were talking about our limit laws and how we had everything in terms of f of x and g of x, well, most of those are pretty much the exact same, except instead of f of x, you have a sub n, and instead of g of x, you have b sub n. So everything like constant multipliers, addition and subtraction, multiplication and division, all of that is pretty much the same. Another thing that we can also apply from our like early limits is squeeze theorem. So whenever we have, so like we said, so earlier whenever we were talking about limits with functions, we said if we have function A, which is in between function B and C, and the limit of B and C is the same, A has to be the same, it's the same concept. So in this case, we have sequence A is less than or equal to sequence B, which is less than or equal to sequence C at pretty much for any n greater than like the initial. And if our limit of a sub n, our limit as n approaches infinity of a sub n is equal to our limit as n approaches infinity of c sub n, and both of those are equal to L, then our limit as n approaches infinity of b is also equal to L. So that's something that you could see potentially when you're trying to solve limits for some of these or solve for convergence and divergence. So there's just a couple other little like theorems and corollaries I want to get to before we have try some examples. So another important one is that states that if the limit as n approaches infinity of the absolute value of a sub n is equal to 0, then the limit as n approaches infinity of a sub n as is equal to 0. So this one is really important whenever you're dealing with oscillating functions, oscillating sequences. So one way that you can notice these is if they have like a -1 to the n or something along those lines. It's essentially something to where it's going to keep shifting back and forth between positive and negative terms. Then another important theorem to know is that the limit as n approaches infinity of k to the nth is equal to 0 if -1 is less than or equal to k, which is less than or equal to, not less than or equal to. -1 is less than k, which is less than 1, not less than or equal to. Sorry, I misspoke on that. And the last one I want to talk about just mentions that if we have if the limit as n approaches infinity of some sequence equals L, then the limit as n approaches infinity of f of a sub n is equal to f of L. So essentially, this one looks kind of weird, but essentially what it means is that we can, as like if we have like a composite function, we can essentially solve for the limit of the inside and then plug that into the outside to find our final like product. So now let's go ahead and then just do a few example problems. All right, so let's go ahead and get started. So we got, so let's go and get started with our first problem. So all of these, we just want to know if the sequence converges, and if so, find the limits. So our first one is going to be, our sequence is going to be a sub n is equal to n to the fourth over n cubed minus 2n. All right, so our first thing we need to do is we need to go ahead and find the limit as n approaches infinity. So if we do this, we get n to the fourth over n cubed minus 2n, which of course will get us infinity over infinity. But one thing we can do, we can either do L'Hopital's or we can just divide everything by the biggest power. So let's actually go ahead and just divide everything by n to the fourth. So we're going to just go ahead and divide n to the fourth over n to the fourth. So n to the fourth over n to the fourth is going to get us 1 in the numerator. Then we're going to get 1 over n minus 2 over n cubed in the denominator. All right, so now that takes care of like everything with L'Hopital's. So we don't have to do L'Hopital's multiple times. So we can go ahead and plug this in. So we're going to get 1 over infinity minus 2 over infinity. And then that's going to go to 1 over infinity is 0 minus 0. So therefore, we're going to get 1 over 0, which is going to approach infinity. Therefore, this one would be divergent. All right, so our next example we're going to do is going to be, we have negative 1 to the nth over 2 to the square root of n. All right, so if we look at this just on its own, it's going to be really hard to find the limit because we have that negative 1. So what we can do is let's actually go ahead and try to take the absolute value. Now, if our limit is not 0, then we have to go back to the drawing board. But if it is 0, then we're good. So if we take the limit of the absolute value of, so if we take the absolute value of this, we're going to get 1 over 2 to the square root of n, because that negative 1, of course, will just go to 1 automatically. So therefore, when we take the limit as n approaches infinity of 1 over 2 square root of n, we're going to go ahead and get 1 over infinity, so therefore 0, and therefore we can say that this converges to 0. This sequence converges to 0. All right, let's try another one. This one, we're going to say that a sub n is equal to 3 to the n times 7 to the negative n. So what we can do first is let's go ahead and rewrite this to get us 3 to the n over 7 to the n. So now let's go ahead and take the limit as n approaches infinity of 3 over 7 to the n. So this one we can't necessarily do anything with just yet, but if we recall, that little theorem that we talked about that said the limit as n approaches infinity of k to the n equals 0, if -1 is less than or equal to -1 is less than k, which is less than 1, well, 3 over 7 fits within that inequality. So therefore, we can say this is going to go to 0. So therefore, we can say this is going to converge to 0. All right, let's try another one. We're going to have 2 to the n minus 1 factorial over 2 to the n plus 1 factorial. All right, so first so there's not really much we can do with this just yet. So we're going to actually have to go ahead, because if we try to take the limit, it's going to be, we can't really do it. So what we're going to have to do is we're going to have to clean this up a little bit. And what we can do is we can actually use the power of factorials to go ahead and do that. So we can see that 2 to the n plus 1 is going to be the bigger term. And we also know that with factorials, you subtract 1 off of each piece. So what we can do is we can rewrite this as saying we have 2 to the n plus 1 times 2 to the n, since we subtract 1, times 2 to the n minus 1 factorial. And our numerator can stay the same, 2 to the n minus 1 factorial. And now we can go ahead and cancel these out to take care of the factorial, because if we can't take the limit of a factorial. So now we can go ahead and take the limit of this new expression. So limit as n approaches infinity of 1 over 2 to the n plus 1 times 2 to the n is equal to 1 over infinity times infinity. So once again, this one will also converge to 0. So I just have one more example before we move on. This one, we have a sub n is equal to the arctangent of the natural log of n. So this one looks kind of weird to deal with initially. However, we can actually use that last theorem we talked about. So what we can do first is we can go ahead and take the limit of our inner function. So our limit as n approaches infinity of the natural log of n is equal to infinity. So now what we can do is we can go ahead and plug this in here. So we can take the limit, so we can take the arctangent of infinity, which approaches pi over 2. And once again, this comes from that theorem that essentially said the limit, let me pull it back up. The limit as n approaches infinity of f of a sub n is equal to f of L. If we know that the limit as n approaches infinity of a sub n is equal to L. So essentially what we can do is we can solve that and then just plug it back in. All right, so now we've kind of talked a lot about convergence and divergence, but now we also need to go ahead and move on to some other aspects with sequences. So there are some other descriptors that we can use. besides just convergent and divergent, since those are, you know, pretty vague. So one thing we can talk about is whether or not they are increasing or decreasing. If a function is if a sequence is increasing, that means that our term a sub n is smaller than a to the n plus 1 for all values of n that are greater than 1. So essentially, it's pretty self-explanatory. Each term is bigger than the last. Decreasing is pretty similar. We can say that our a sub n is bigger than the subsequent term n plus 1 for all n is greater than or equal to 1. Once again, pretty self-explanatory. And then we have monotonic. And that essentially, if a sequence is monotonic, it just means that it's increasing or decreasing. Another thing that we can use to describe sequences has to do with bounds. So, a sequence a sub n is bounded above if there is a number such as this uppercase M such that our sequence is always going to be less than or equal to that number n for all n is greater than or equal to 1. Similarly, a sub n is bounded below if there is a number such as small, like lowercase m, such that m is less than or equal to a sub n for all n is greater than or equal to 1. And then we can say that a bounded sequence is bounded above and below. And another theorem deriving from these two descriptors states that every bounded monotonic sequence is convergent. All right, so now let's go ahead and do a couple of examples with this before we go ahead and move on to our next section. So our first example, we want to know, is the sequence increasing, decreasing, or neither? And we also want to know, is it bounded? All right, so let's go ahead and our sequence in this one is going to be a sub n is equal to 1 minus n over 2 plus n. All right, so our first thing we need to do is figure out, we can figure out whether or not a function is increasing or decreasing. One thing you can do is you can go ahead and convert this to a function, like a function of x, and then just kind of just do like first derivative test. But in your book, it looks like they want you to actually try something a little bit different, and we're going to go ahead and do that version instead. So what they want you to do is compare your initial function, your a sub n, to a sub n plus 1. So we're going to have 1 minus n plus 1 over 2 plus n plus 1. And we can use n plus 1 because essentially this is going to kind of be, the same pattern for every value of n. So if we go ahead and rearrange this, we get 1 minus n plus 1. So that 1 and that negative 1 will cancel out to get us negative n over, we get 2 plus n plus 1, which gets us 3 plus n. So if we look at this, we can see that 1 minus n is greater than negative n, and we also can see that 2 plus n is less than 3 plus n. So if our numerator is bigger, so if the numerator, if the numerator is bigger, then that indicates your function is the fact that our numerator of our first one is bigger than our second implies that the first is going to be bigger, and then once again implies that it's essentially going to be decreasing as we move on because our numerator is getting smaller. And then if our denominator gets bigger, that also implies that your function is decreasing. So therefore, we can say that 1 minus n over 2 plus n is greater than negative n over 3 plus n. So therefore, we can say that we are decreasing. That's based on our initial definition of increasing and decreasing. So now we have to figure out our bounds. So usually with your bounds, usually what you want to do is you want to look at your first term and your infinite term. So your A1 is going to be 1 minus 1 over 2 plus 1, so 0 over 3. And then you want to look at your A sub infinity. So you're going to take your limit as n approaches infinity of 1 minus n over 2 plus n. You're going to get negative infinity over infinity. Do quick L'Hopital's. Limit as n approaches infinity of negative 1 over 1 equals negative 1. So therefore we can say that we are decreasing, and we are bounded between negative 1 and 0. All right, so our last example is going to say states that we know that a sub n is decreasing and is bounded between 5 and 8. What is the limit? All right, so if we think about this, we can go ahead, we can say that we have two lines. We have, this is 8, and this is 5. And we also know that our sequence is going to be decreasing. So we're going to kind of just, show that we're decreasing from 8 to 5. But because we're bound, we can't get any further below this, below 5. So therefore, we can assume that it will be approaching 5. So therefore, we can state that our limit is 5. And this kind of makes sense. We also had that theorem earlier that said every bounded monotonic sequence is convergent. So essentially, if you have a bounded increasing function, you will go towards the upper bound. If you have a decreasing bounded function, your limit will be the lower bound. All right, so that's all I have for section 11.1. Let's go ahead and move on to 11.2. So we are at 11.2, which is over series. All right, so what this one states, so let's go ahead and think about this. So if we add every term of a sub n, we get a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. And hypothetically, we can think and imagine that we get all the way to a infinity. Well, whenever we go to a sub infinity, that's actually and we add all those together, that is what is called an infinite series. But in most cases, it's really hard to go ahead and actually find your infinite series and just plug everything in, because if you have infinite terms. But what we can usually do is we can go ahead and think about things in partial sums. So yeah, we have this infinite series, which is essentially, the sum of every term. But we can't always, find the sum of every term. So what we can sometimes do is we can use partial sums. And those are essentially, those are used whenever you're just adding a few terms, adding a few terms out of your sequence. And usually, after a certain point, this can be used to approximate your total sum. Because if we think about it, we can get your first partial sum is just your first term. Your second one is your first 2 terms. Your third is your first 3. Your fourth is your first 4. And you can just kind of, keep going on and on and on and on. And essentially, we have this partial sum of your nth term, which is essentially the same thing as saying that we have a summation of I equals 1 to n of a sub I. So going off of this, we can actually go ahead and use this to talk about convergence and divergence. So what we can do is we can say that if our set of our partial sums, if our partial sum sequence is convergent, And the limit as n approaches infinity of our partial sum sequence is equal to our actual sum, and like that exists as a real number. The summation of a sub n is convergent, and it's going to go ahead and be convergent to our total sum. So we can go ahead and actually use this to go ahead. So if we know our S sub n sequence, it's actually not that hard to go ahead and find our total sum. So we're just going to do a really quick example of this because we have a lot more need to get through. So example, it's like, what is S when S sub n is n squared minus 1 over 4n squared plus 1. All right, so we can do our limit as n approaches infinity of our S sub n function of n squared minus 1 over 4n squared plus 1, infinity over infinity. We're going to go ahead and just divide everything by n squared to get us 1 minus 1 over n squared over 4 minus 1 over n squared to get us 1 minus 0 over 4 minus 0, so 1/4. So therefore our sum is just 1/4. All right, so our next topic that we need to go ahead and cover is geometric series. And this essentially is, these are going to be in a special format. So you're going to have your summation from n equals 1 to infinity of some number a times r to the n minus 1. And a cannot be equal to 0. So whenever we have this, r is going to be what is referred to as the common ratio, because we're going to be multiplying each term times that ratio. Your partial sum is going to be a times 1 minus r to the n over 1 minus r. And we can, if you go ahead and derive that, your total sum is going to be equal to a times 1 minus r. And lastly, these converge if and only if the absolute value of r is less than 1. Otherwise, it'll just diverge. All right, so we're going to go ahead and just do a couple quick examples of these. So for these, we just want to go ahead and figure out if they're convergent or divergent and find their sum. So our first one is going to be -3 to the n minus 1 over 4 to the n. All right, so of course we need to be in the form a times r to the n minus 1. So we have an n minus 1, but we also have an n. But this actually isn't that hard to work out, because what we can do is we can actually pull a 4 out and say that we have 4 times 4 to the n minus 1. So therefore we can rewrite this as -3 to the n minus 1 over 4 to the n minus 1 times 1/4. So now, and then we can, of course, we can combine the -3 and the 4 to get us 1/4 times -3/4 to the n minus 1. So now we are officially in our form. We know that our A is going to be 1/4 and our R is going to be -3/4. We know that the absolute value of -3/4 is less than 1, so therefore we know it's going to converge. Now we can go ahead and find our sum. So therefore our sum is equal to A times 1 over 1 minus R. So therefore our A is going to be 1/4 over 1 minus -3/4. So no, that's going to be 1 plus 3/4, so that's going to get us 1/4 over 7/4, which will go down to 7/4, and that will be our final sum. We're going to do another example. In this one, we have e to the 2n over 6 to the n minus 1. Now the issue is we now have that 2n, but this once again actually isn't that hard to mess with because we can use our properties of exponents to go ahead and actually split this into e squared to the n over 6 to the n minus 1. We can then do the same little trick that we did in the last one and pull out an e squared. To get us e squared over 6 to the n minus 1. So now we have our a is equal to e squared and our r is equal to e squared over 6. Now our, that is actually going to be approximately 1.23. R is going to be greater than 1, so therefore this is the divergent and we can stop here. All right, so now we've kind of gone over geometric series, but it's also important to remember that not all series are geometric. However, we can go ahead and get creative and we may be able to solve for some of the other sums using other methods. So one example is partial sums and partial fractions, but there's also some other theorems that are also useful to let us help us figure out convergence, divergence, and maybe even sums. So usually it's good to figure out whether or not your function is convergent or divergent first. That way you don't waste your time trying to figure out a sum that just does not exist. So our first theorem that we want to cover states that if we have a series for a sub n is convergent, then the limit as n approaches infinity of a sub n is equal to 0. Conversely, in our test for divergence, it states that if the limit as n approaches infinity of a sub n does not equal 0, or it just does not exist, the series will be divergent. And this makes sense. So let's say, for example, our sequence or our series, the limit of our sequence goes to 1. But the thing is, you have infinite terms, and that when you're adding that up, you're doing 1 plus 1 plus 1 plus 1 infinite times. Therefore, you will still get to infinity, and that will diverge. Whereas if you go down to 0, hypothetically there may be a stopping point somewhere to where you can say, okay, boom, here is the sum. And it's also important to note that you can break down series. And essentially what you can do is you can either pull out a constant multiplier, and you can add and subtract, or you can add and subtract series. So you can split them up through addition and subtraction. All right, so I want to go ahead and just do about a few more examples of some series. Once again, we just want to figure out if these are convergent and divergent, and then find the sum if they are convergent. So in this example, we have 2 plus n over 1 minus 2n. So we can go ahead and let's go and first do our test for divergence. Is usually a good place to start. If it's easy to plug in, that way we can go ahead and see if because if it's automatically divergent, then we're good and we can stop. So 1 minus 2n, infinity over infinity. L'Hopital's, we can get 1 over negative 2. So therefore we get negative 1/2, and since that is not equal to 0, this one is just going to be divergent. For our next one, we have 2 to the n plus 4 to the n over e to the n. So this one's actually kind of nice because what we can do is we can actually go ahead and split this one up to get us 2 to the n over e to the n plus 4 to the n over e to the n. All right, so now we can go ahead and rewrite these to get us 2 over e times 2 over e to the n minus 1. And over here we can get 4 over e times 4 over e to the n minus 1. So our first thing we need to do is we need to check to see if these are going to be convergent and divergent. So e, I believe, is approximately 2.7-ish. So if we go ahead, we can get 2 over 2.7 is less than 1, so we're good. The thing is, but now we have 4 over 2.7, which is greater than 1. So even though this piece on the left will converge, the piece on the right will diverge. And similar to improper integrals, if one of these diverges, the whole thing must diverge. All right, and now we are down to our last step. We're going to do one last example, and this one's going to be a little bit different. And you'll see what I mean in a minute when we start it. So in this one, we have 2 over n squared minus 1. All right, so on a lot of these other examples, what we were able to do was we could either convert these to geometric, but there's no way we can do that. And I'm not going to bother solving the limit, like showing it, but it's pretty obvious to see that this one will actually go to 0, so we know it's not automatically divergent. So what we're going to have to do is we're going to have to get a little bit creative. So this is when, so you know how I kind of offhandedly mentioned partial sums and just kind of adding, partial fractions and partial sums, this is one of these examples where this can come in. So what we can do is we know we can factor out n squared minus 1 to get us 2 over n plus 1 and n minus 1. And now let's go ahead and use partial fractions to go ahead and break this up. So therefore we have 2 is equal to a times n minus 1 plus b times n plus 1. All right, so if we do n is equal to 1, we eliminate a and we get 2 is equal to 2b. B is equal to 1. If we do n is equal to negative 1, we get 2 is equal to negative 2a. A is equal to negative 2. Negative 1, All right, so now we can say that this is going to be negative 1 over n plus 1 plus 1 over n minus 1. So now what we can do is let's go ahead and start listing out, do some partial sums. We're just going to list out the first few terms. So if we have when n equals 1, we can get negative 1 over all right, so yeah, we start off with n equals 1, so we get negative 1 over, give me just like this second. Oh, I miswrote it. Okay, there we go. I was like, I knew I had a mistake somewhere. This is it. Okay, this one we start out at n equals 2 because our series don't always have to start out at n equals 1. And I was like, wait, this doesn't make sense in my notes. But there we go. I found it. So we can go ahead and get negative 1 over 2 plus 1, so negative 1/3, plus 1 over 2 minus 1, so plus 1 over 1, plus, we're going to get negative 1 over 4th, plus 1/2, plus negative 1/3, negative 1/5, excuse me, plus 1 over 3, plus negative 1 over 6, plus 1 over 4, plus negative 1 over 7, plus 1 over 5, and we know this is going to keep going on and on and on. But if we look at this, we can see an interesting little pattern here. We can see we have a negative 1/3 right here and a 1/3 right here, so we can say that these will cancel out. We have a negative 1/4 and a positive 1/4, so these will cancel out. We have a negative 1/5 and a 1/5 that will cancel out. And because the series will keep going on and on and on, we can assume that this negative 1/6 and this negative 1/7 will get canceled out. So because of the way this function works, because everything will eventually kind of get canceled out when you start looking at your partial sums, everything will get canceled out except for these two terms, 1 over 1 and 1/2. So we can just go ahead and add those together to get our final sum is 3/2. All right, so that is actually all that I have for today. Good luck for everything on the rest of the semester, and yeah, have a good day.